Thank you for the introduction. I'm very grateful for the organizers for the provided opportunity to make a talk and to present you not only the kinetic surface model, but also touch the FESTIM project. To start with, hydrogen transport is an important question not only in nuclear fusion, but also in other research fields, such as hydrogen energy, of course, and material science. And in general, when we face a real application applied problem, we end up with some numerical tools to simulate the hydrogen transport in different parts, and for example, the first wall of a device. And there are a couple of different simulation packages, starting from very good commercial ones, some are private, that are developed in separate laboratories, and now more and more packages that are openly available appear, and even today there are in fact two simulation packages for hydrogen for modeling hydrogen rotation that are presented at this conference. But I will talk about FESTIM, a finite element code for hydrogen transport simulations in materials. FESTIM in general solves a hydrogen transport problem that is defined according to McNabb and Foster model that includes hydrogen diffusion due to different mechanisms such as concentration gradient or temperature gradient, and also trapping detrapping from defect sites. And this hydrogen transport problem is coupled to the heat transfer, and as any system of partial differential equations, you have to put some inputs to define and fully pose your problem, and then with FESTIM you can get the temperature and concentration fields, and also acquire some post-processing on a request. FESTIM has been under development since 2019. It's fully written in Python, making it very user-friendly. It uses the Phoenix library to solve partial differential equations. And since 2024, the FESTIM project is NumFocus affiliated. The most important part of FESTIM is its open source nature, and the code has been verified and validated to prove the reliability to the users, and currently it's used worldwide in more than 27 different organizations. Another important part of FESTIM is its community, and for the users there is a complete documentation about different parts of the code, as well as subsequent guides for the users and the developers. For user support, there are two possibilities, namely the discourse forum and the Slack channel. And also for newcomers, there is a FESTIM workshop that can be used to get in touch with the code. And also this workshop has been held in several organizations by developers on site. And to show the capabilities of FESTIM, I'll present some published use cases. And I believe one of the most common is reproduction of laboratory experiments, where the model usually includes both phases of sample preparation, starting from the exposure phase and ending with the, for example, thermal desorption spectroscopy analysis. And that is the results from our great German paper, where the final TDS spectra has been fitted automatically. And by fitting, I mean parametric optimization of input parameters for the model. And for the users, there is a special example that show how this parametric optimization can be done. The next impressive case is related to the work of Remy on hydrogen retention in ether diode monoblocks. It's a full 3D model, well, not full, but a part of it due to some symmetries that also include 3 different materials with the special treatment of interfaces. The next also very impressive example is simulations of simulation of tritium transport in a demo breeding blanket performed also by James. And this example included a complex 3D geometry, several materials, and also the hydrogen transport problem was coupled to the fluid dynamics to account for the advective tone. A more recent example is the HISP project, where HISP stands for Hydrogen Inventory Simulations in Plasma-Phasic Components. And this work is done by Kailin Daniel and is done for ITA, where the work includes discretization of the full ITA first wall by one-dimensional bins, in which bin hydrogen rotation is simulated and estimated to determine the most effective ways of removing tritium from the first wall. And the more information you can get from Kailin directly, I believe, or check her poster that also was presented at this conference. The last case that I would like to mention is dedicated to my work on laser-induced desorption from tungsten films, and represents application of FESTIM to modeling of hydrogen release under impulse heat laws. More information also you can find in my poster. Overall, FESTIM, the current stable version of FESTIM, has a wide functionality, but it also has several limitations, such as poor parallel scaling, some technical debt, making it more and more difficult to implement new features. Some physics is missing, such as multi-level trapping in defect sites, and also the main issue is that the Phoenix legacy is not maintained anymore. However, all of these issues will be resolved in the upcoming major release of FESTIM 2 that is based on the up-to-date version of Phoenix X. And recently, the alpha version of FESTIM 2 has been released, and as I've shown by the HISP project, you can already use it. However, the stable version is also maintained, and in FESTIM 1.3, we implemented a kinetic surface model that allows to account for surface processes. And these surface processes become important under certain conditions. For example, in the experiments on hydrogen uptake from the gas phase, when the energy of incoming molecules is low, so the molecules adsorb on the surface and then only absorb into the bulk. And the example that I like the most is that surface processes play the crucial role in the formation of molecular hydrogen in interstellar environment, since molecular hydrogen more effectively forms on the surfaces of dust grains. And there are a lot of surface mechanisms that sometimes should be considered, apart from classical, I would say, dissociation and the Levmira-Hinch-Wooldt recombination, which is recombination of two adsorbed atoms. And to account for all of these processes and make the model as flexible as possible, I should say we attempted to make it as flexible as possible. And the model itself is based on the approach of Pick and Sonnenberg, and involves introduction of additional hydrogen species, namely the adsorbed hydrogen. And the evolution of the surface concentration is in the current implementation is mainly driven by the flux balance at the surface, meaning that the current implementation is limited to one-dimensional hydrogen transport simulations, since it's a coupling of 0D surface model and 1D hydrogen transport model. And to make this model flexible, we implemented an arbitrary function that defines GVS, that defines all possible surface mechanisms that determine desorption and adsorption, and rely on the temperature and concentration of hydrogen. The implemented model was verified and validated. The verification was done using the method of manufactured solutions when we literally manufacture a solution that satisfies our governing equations, use it to determine suitable boundary initial conditions and the source terms, and use them in our simulations to obtain a numerical solution, and then compare the manufactured solution and the numerical one. And here the result of verification showing a very good agreement between exact and the numerical solution, and suggesting that we implemented the model correctly. Validation was done against 4 experiments. The first one is the isothermal absorption of hydrogen in titanium that was conducted at 5 different temperatures. It's a relatively simple case since no traps were considered in the bulk, and there are only 2 surface processes, namely dissociation of hydrogen molecules and recombination of Legmore-Hinch-Wood type. And in figure, you can see that FESTIM reproduces the results very good. Right. The second case is reproduces the results on adsorption of deuterium on oxidized tungsten that were conducted at the room temperature. So no absorption. No absorption was considered, and the surface processes are the same as in the previous case, but we considered the dependence of the desorption energy or on the local coverage of hydrogen and oxygen, making this a highly nonlinear problem. And in the figure, you can see a comparison of, in the top figure, you can see the comparison of FESTIM results with the experiment, and we were able to compare the results of FESTIM with the ones obtained with other simulation code means. And the correlation between 2 codes is excellent. The third case is a more complex one. It reproduces the results from the experiments on the tungsten exposure with low energy deuterium ions. And the important feature is that tungsten samples were pre-damaged with highly energetic tungsten ions, and therefore in the simulations we used 5 different traps and considered 3 different surface processes, namely adsorption of atoms, desorption of molecules, and the second desorption of mechanism of desorption that corresponds to Eley radial type, when one incoming atom recombines with one adsorbed atom. And in the figure, you can see a comparison of FESTIM results with the results from MEMS, and also with the results of nuclear reaction analysis. And in both cases, we obtain reasonable agreement. Finally, the final case reproduces the experimental data on deuterium implantation in European steel that was also damaged with the tungsten ions. The model is relatively the same as in the previous case, but here we performed additional comparison with the FESTIM X code. And although the agreement with the experiment is quite reasonable, the correlation between FESTIM and FESTIM X is almost perfect. And here comes the conclusion. In short, kinetic surface model was implemented in FESTIM. It's available to all the FESTIM users. We verified and validated it, and the most important part is that all of the presented results are openly available and 100% reproducible. And you can run all of the scripts in your browser via Binder. We have some future plans for this model. As the next generation of FESTIM is being developed, we plan to port this model to FESTIM 2 and also consider several steady-state approximations that can accelerate simulations with this model. And also we think of extending this model to higher dimensions to analyze the effect of surface diffusion on hydrogen rotation. With this, I'd like to thank you for your attention. If you have any questions, please feel free to ask them.
Thank you very much, Vladimir. That was some really nice slides, really nice talk. Thank you very much. So yeah, we have a couple of questions already in the Q&A, so we can dive straight in. First up from Casey, we have for the MMS verification exercise, did you perform any convergence studies, spatial or temporal?
So yeah, we definitely performed the temporal study, and we observed that the relative error between the MMS, between the manufacturer solution and the numerical one decreases with the step size. And the same is what observed by me in regarding the mesh convergence.
And then also from Jonathan, sorry, someone else wanted to. So from Jonathan, we have, can you please explain a bit how you did the migration from FESTIM V1 to FESTIM V2 in practice?
So, yeah, a bit difficult question for me, but in fact, maybe Remy or James will answer if I will be incorrect. But currently, both versions can be installed via Conda, for example, and you can specify which version will be installed depending on by providing it to the Conda command, right? Am I correct, James?
Yeah. So we do have an alpha version of FESTIM 2.0 out. And regarding the migration, basically we're just changing the underlying engine, right? So we're going from using legacy Phoenix to the new Phoenix X FEM software. And yeah, it's going very well so far. And feel free to check out the repository to see the progress. And we do have some projects like outline the progress we've made.